문제가 없군요. 없어도 진행을 하도록 하겠습니다. 저번에 우리가 그게 없었잖아요. 네, 스케치북이 없었는데 다시 한번 찾아볼게요. 원래 이렇게 스케치북이 이상하다. 원래 있었던 것 같은데. 뭐라고요?
혹시 영어로
아, 그래, 그런 건가요? 해볼까요? 스케치. 이거 정말 이상한데요. 이게 아니군요. 혹시 그러면 그쵸. 요거를 작성 다운을 받읍시다. 받으면 되잖아요. 그쵸? 윈도우 이게 저 구글 플레이를 요거요? 그렇군요. 전 당연히 애플일 줄 알고 무료 다운로드 허허 뭐죠? 무료 다운로드라고 해서 다운로드를 받으려고 했는데 다시 한번 해보고 안되면 저번처럼 그대로 가도록 하죠. 이 앱을 소유하고 있습니다. 벌써 설치가 끝난 건 아니겠죠? 그렇죠. 없습니다. 그러면 그냥 캡처를 해서 저번처럼 할게요. 캡처 및 스케치. 새 캡처. 이렇게? 이거 조그만. 네, 그렇습니다. 이게 참 뭔가 마뜩지 않지만 어쩔 수 없군요. 자, 그 전상공 씨는 어디 갔어요?
카톡을 해봤는데 읽질 않습니다.
그렇군요. 알겠습니다. Okay, although Mr. Chong is not here, but we have to proceed. So this is lecture 15. So I want to ask you whether you have already done your homework number 14. How was your homework 14? So okay, so previously the homework 14 was to make just a dummy framework for transient simulation. So now, for example, if you give certain kind of input voltage, let's say the input voltage in a arbitrary form like this, then your simulator can generate the any quantity output, for example output current like this way. So that is possible for now your homework number 14. So now we'll think about more realistic one. So now let's say that we just apply one pulse. So pulse is applied just like previous example, but let's just say that this period or just the duration of our pulse is kind of microsecond. Yes, so it is corresponding to, for example, 1 megahertz signal. In this case, yes, 1 megahertz is not that high frequency for a device considered in this work. So yes, so that then you will find that the actual result, the accurate result will be quite similar to your calculated result. But instead of that, instead of this 1 microsecond, now you reduce it by 1 nanosecond. So now it is corresponding to a frequency of 1 gigahertz. Yes, even this 1 gigahertz to you, that's not that high, but we can proceed with this type of scaling. How about 0.1 nanosecond? Now it is corresponding to 10 gigahertz. So we can always proceed quite easily, even higher frequency. Okay, so then if we are working with low frequency, then maybe our quadratic approximation is good for our application. However, if we go to really high frequency application, then certainly our currently built code is not sufficient to get the correct solution about your application. Okay, so however, I wanted to emphasize one more thing. Even at low frequency like 1 megahertz, sometimes we need a certain quantity. Think about this case. This is a really practical case we are working with. So think about a DRAM. So you have a DRAM and you wanted to calculate the capacitance inside the DRAM cell. So of course there is a well-defined capacitor which is intentionally introduced in your system. So DRAM has one transistor and one capacitor in its structure, so you have to know the capacitance of your capacitor. Yes, usually this is well known. However, unfortunately DRAM itself, so when I say DRAM, there is one transistor, and in this case this transistor itself contains many parasitic capacitance in it. So the point is, we have to find out how can we consider or calculate this parasitic capacitance. Otherwise, our estimation of retention time regarding to this external capacitance, that does not give us the exact result for our DRAM retention property. So data retention in this case, in the case of DRAM, data retention is like this. now you store the energy or the charge in your external capacitance. Yes, there is one capacitor and there is also another transistor here. And once you write, oh, sorry about that, here I have to say over cos minus sign instead of positive sign. Yes, you store the charge here and just to turn this means that this transistor off. So now think about the case. Since the charge is stored here, so you can easily find that yes, the potential at this node point will be quite high because yes, we have stored the data, and since we have to apply off condition, so usually the gate voltage of this device, this transistor, will be low. Yes, so now we have typically this situation. So if our transistor is really perfectly turned off, then our data stored in this capacitor will stay forever. However, unfortunately, we know that there is certain amount of current due to our leakage mechanism. So yes, the stored data is just leaked by this leakage mechanism. So if we observe, for example, stored charge as a function of time, and this is time 0, after that we will have a reduced number of charges stored in our capacitor. So think about this one. Maybe we have a certain boundary for determining this is on or off or 0 and 1. So if the stored charge is beyond this value, then we'll say that this is corresponding to logical 1. And if we have the charge below certain level, then we'll call it as logical 0. So simply speaking, this reduction of stored charge is corresponding to the weaken or becoming weaken, more weaker in terms of data reliability. So yes, this is a strong one. But if your data is approaching to this point, then is it really 1 or 0? Yes, it is 1, but I'm not quite sure. And how about this? In this case, you will have 0. Now you have a failure. After that, eventually, when you have this point, certainly you just there is the loss of your data. Then what will happen in your DRAM? Your bit previously 1 now changed to 0. So can you live with such kind of system? So you just write something, but after that, yes, everything is just 0. You remember that somewhere there I wrote 1, but the computer memory does not say that I have 1 inside my memory. So that's not possible. So people, unfortunately, in the case of DRAM, in order to prevent this kind of unwanted behavior, yes, they just make a certain time. Okay, after a certain time, maybe the stored charge will be discharged considerably. So our bit 1 becomes too weak. So instead of that, instead of just leave it there, so sometimes, so everybody now write again. So it means that after some time later, so DRAM cell just check whether this is 1 or not. So if this is 1, then it just write it again. So after this procedure, then what will happen to your DRAM? Then your DRAM bit becomes once again stronger. So of course in this case you have to write it again, and again it will move down, and after same time period is written again, written again, written again. So now you can easily understand in the case of DRAM you have to quite frequently check the status of your DRAM cell and also write it again and again. What happens? This is a kind of sometimes redundant operation. So if your device is perfect, then maybe your data stored in this capacitor will stay forever. However, the point is, since our device is not perfect at all, that's the reason why we have to refresh. So refresh our device, so that if we have to do this refresh job again and again too frequently, so then it is directly related with the increase of our power consumption, because in order to write something, then you have to spend a lot of energy to write this bit. So point is, when you consider this DRAM operation, you have to find out the time where your device or your cell takes the originally bit 1 for 1. So that is quite much important. But which one really determines the time dependent behavior? Of course, this C determines the initial condition. However, when we consider the behavior of our system, also the capacitance inside this DRAM transistor really plays an important role, because yes, that makes a certain impact on transient behavior. So what is my conclusion? Even in the case of this quite a low frequency case, we have to consider certain kind of capacitance. We need to calculate capacitance component inside our transistor. That's the point. The frequency can be as low as, for example, 1 megahertz. So yes, in the case of 1 megahertz, is there any kind of a transient effect? So then I have to say usually not. But however, we have to evaluate the capacitance exactly. So then how can you, for example, calculate the capacitance? So what is the capacitance? Actually, in the case of our multi-terminal device biased at non-equilibrium case, then it is not that directly possible to measure certain capacitance. So the way is like this. First, evaluate your Y parameters. So I have to start with Y parameters. What is Y parameter? Y parameter means that, so let's say something like this. Y parameter, there are family of parameters, but the family is made of this way: alpha and beta, and this alpha and beta are corresponding to terminals. So let's think of a 3-terminal device: source, gate, drain. Then alpha can be source, gate, drain. Also beta can be source, gate, drain. So now you understand. For example, we can think about YDD, YGG, and YSS, which are corresponding to the self quantity. So you apply something to certain terminal and observe something at the same terminal. So there are three of them. Also, you can think about this kind of thing: D, S, G, D. Okay, so are you with me? So G, S, G, D. So we can think about such kind of non-diagonal component. So here non-diagonal means that this and that they are different and they are the same. So you can think about so in this three terminal case, you can think about 3 by 3 different quantities. So in total 9 different quantities. So roughly you can think about a matrix which is given by y something, y something, y something. So let's say y ss, so gg, dd, and sg, sd. You can easily understand, yes, there will be such kind of 9 components for your y parameters. Okay, so do you have any questions? So yes, but up to now I have not explained what is the physical meaning of this y parameter individually. So for example, what's the meaning of ygg, ydd, or other off-diagonal component? Then let me just explain it from now on. So now when we have y sub alpha beta, then we can think it in this way. So this is corresponding to a ratio between delta I over delta v, but delta I, the voltage excitation, is applied to beta terminal, and you observe the fluctuation or response of your terminal current at which terminal? So now alpha. So this is corresponding to the y parameter defined at alpha beta configuration. So of course, so we are now assuming that we are applying a sinusoid signal into our system, and since the system is linearized, since the applied voltage fluctuation is so small, so we can treat this system as a linearized system. So of course they assume certain frequency, angular frequency omega. So it means that in our case, 1 megahertz case, we are now assuming that omega is given by 2 pi multiplied by 10 to the 6 second, corresponding to 1 megahertz. Of course you can change it. So anyway, that's it. That's it for our y parameter. Then maybe you remember that one of the most important quantity when you characterize your transistor is the GM. So do you remember GM? Transconductance. And the definition of transconductance was like this: delta VG and delta ID. At which frequency? At omega equal to 0. So at an extremely low frequency, actually at DC condition, we can evaluate the response of drain current with respect to the gate voltage excitation. This is definition of GM. So now you can easily understand. Now this is corresponding to what? So this is corresponding to y dg at omega equal to 0. That is the GM. Of course, I have to be more careful. GM is a real scalar number. So transconductance written in Gmans, this is a real number. However, in general, Y parameter can be a complex number because we apply a sinusoidal input and just to measure this also sinusoidal resultant sinusoidal output, and they can have phase difference. So in order to represent such kind of a phase difference, we have to introduce a complex number. So think about this one. Yes, certainly this one in general it can be a complex number, and in general, yes, this is a real number. What is the difference? Because at the low frequency we will have just in phase component, of course, because we are just to wait forever for applying certain voltage, so they are always in phase. So in this case we have to say this is the form of energy component. Okay, then also think about this one. Now we can think about another important quantity. So actually another important quantity like CGG. So CGG. So what is this? It means that we are now think about what is the gate capacitance. If we change something at the gate terminal, then how much charge is collected by this voltage application. So how can you calculate this CGG component out of our Y parameter? Obviously, you know that this is corresponding to YGG parameter. However, if you, for example, yes, so YGG parameter and its real part, no, this is not the case. So real part is corresponding to in phase component, but please think about this case. Now you have a capacitor called CGG and you have biased ground and apply delta V. Then what will happen? In a phase notation, you will have the current I, delta I, corresponding to J omega C G G. So now you understand. Oh, sorry about that. Multiplied by, of course, delta V. So taking from this simple system, then when you take delta I over delta V, then you will find that this is corresponding to your CGG. So in order to calculate this CGG component, actually you have to find out certain quantity corresponding to the imaginary part of your Y parameter. So simply this will be like this. You take your YGG and divide by J omega and take its real part, real of this one. Or sometimes you can say that instead of taking real part, you just take the imaginary part of minus. That can be also the way you can calculate this number. Okay, so simply speaking, so in a simple way, let me just summarize. So people try to consider in this way. Y parameter is given by, for example, the conductance parameter. This is corresponding to the real part and alpha beta, and also taking J omega and C alpha beta. That is the expression. Of course, here we have to have the imaginary part here. So the imaginary part of Y parameter will be given by omega c sub alpha beta. So now we can calculate it. So now it becomes quite obvious that even though we are working with quite a low frequency, like even 1 megahertz, then we have to be able to calculate the out of phase component, which is not available to us with the quasi-static approximation. In the case of a quasi-static approximation, we simply assume that omega equal to 0, so C sub alpha beta component cannot be obtained from this quasi-static approximation. So that's the reason why even at low frequency, although we are not working with extremely high frequency device, but still we have to have calculated this transient behavior. So are you with me? Also another one would be, of course, if we are working with the RF device, then the transient simulation is at the heart of that device application. You have to be able to find out the response of your device with respect to the frequency. So if your device is operated at extremely high frequency, what will happen to your device? That should be simulated by your device simulator. But that is one thing. Another. And now I think that you are fully motivated to start your implementation about, you can say, the fully functional transient simulation instead of much simpler one with quasi-static approximation. So now you have your homework, so homework number 15. So please implement the fully functional transient simulation. So the bias condition is the same as before. So just to take the VDD for your drain voltage and just to apply one pulse, gate voltage pulse into your double gate MOSFET and try to find out the result. However, in this case, previously we just assumed about 1 megahertz signal, so as an input pulse. Then please change your time scale. So you can use, for example, so 1 second time scale. So what is exactly 1? So we have to be careful. So let's say that this is corresponding to 1 second, 1 millisecond corresponding to 1 kilohertz, microsecond, nanosecond, and increase it further. So now you will find that your device is working quite much differently when you apply this kind of behavior. So of course, if your signal is so slow, then you will find that okay, also your current will follow same time stamp. However, now your operation becomes faster and faster, then eventually you will find a certain delay of your device operation, because now output input signal is too fastly changing, so it takes some time for your device to follow its motion. So you will have different behavior. So please report the change of transient output waveform. So that is homework. Then up to now we have discussed about Y parameter. So the important quantities are Y parameters. Also from Y parameters you can consider conductance parameters and also capacitance parameters. They are usually important for your application, and I just gave you homework number 15. Then what's the next? Up to now I have not discussed about how can you actually implement the transient simulation. I just sketched that if you can you can do the transient simulation, you will get a lot of benefit out of it. Yes, that's true, but how can you actually implement this transient simulation? That is the main topic of today's lecture. Okay, the term which was neglected in your previous lecture or previous assumption of quasi-static approximation was, yes, time derivative of any quantity in your equation becomes 0. This is the case. But since now we are working with a transient effect, so assuming this time derivatives must vanish doesn't hold at all. So now we have to find out how can we properly implement our time derivative operator into our system. So maybe you remember that in our case we are taking certain strategy called time marching. So instead of considering all available time points, that is not our approach. We just consider starting from initial time step, then yes, go to next time step. That is, this marching is our strategy. So during this time marching, the information available to you is, yes, the current bias condition. For example, gate bias voltage is 0.5 volt and drain is 1.0. Then how can I solve it? Previously you just neglected any kind of transient effect, so just considering the present bias condition, that was enough for your application. But think about now this a fully functional transient simulation, then not only the present status but also your previous status will make effect on your solution. So that is the point. So time matching here, so in this time matching approach, your round over round t should be discretized in terms of your present solution and your past solution. Okay, you can take many different past point time instances, so sometimes it can be plural form, or sometimes if you take just last solution point, then you can take only one past solution. So that's the point. So now let's think about this one. However, I wanted to say that this is all corresponding to, before starting our today's main lecture, so I have to say that when you try to discretize this time derivative operator, we can find two different groups for discretizing this system. So please note that there is something called explicit method and implicit method. What's the meaning of these two terms and how can we have the difference? So let me just explain it. So I'm not quite sure I can deliver their difference quite well, but let's just try. So think about certain quantity A. Now we wanted to take so don't be confused with any matrix, so I just introduce A to represent any quantity. So let's say A and try to calculate its time derivative. Then how does it look like? by definition, so we can think that, okay, delta t goes to infinitely small, and we can think about delta t and a quantity at t plus delta t minus a quantity at t. That is the definition of our time derivative evaluated at time t. So, yes, quite frequently when we have a spatial derivative, if we have such kind of a limiting procedure, then what we assumed was, okay, this is not achievable for our discretized manner, so let's just drag it and assume that, okay, our, how can I say, our difference or spatial resolution is fine enough, so we can safely neglect this limiting factor. This is always guaranteed, already guaranteed by our fine mesh. Just like this in the case of spatial dimension. Now when we go to the temporal dimension, we just take this approach. So think about this one. Now we can think about ti plus 1, which is discretized time point, and ti, yes. Also we can think a quantity at t sub I plus 1 minus t sub I. It looks great. Yes. So of course, if we have quite small distance between t sub I plus 1 and t sub I, then yes, this limiting approximation can be satisfied. However, we are not quite sure whether which one is sufficiently small or which one is too large. But anyway, this is the approximation we will take. Yes. So now let's say that this is the case. And in this case, we just relating two solutions in order to calculate our first derivative. Yes, this is a time derivative, and we are only taking one time step, and it's a 4 more time step. This kind of approximation or this kind of approach is called as Euler method. So Euler method is the simplest one we can invent for our time derivative. Then of course your obvious question is there any method or methods which are beyond the Euler method? Yes, there are plenty of them. So if we include more and more previous time instances, then it becomes more and more accurate, and there are so many specialized names or approaching methods for this time derivative. So yes, however, for a while we will just stick to the Euler method. Is not because Euler method is the best. Okay, actually Euler method is the worst. So as you can see, since it considers only 2 time points, so it is really a crude approximation for time derivative. However, since it is the most simple one, so we will stick to this one for a while. So now think about this one. Okay, good. Now let's try to evaluate something. So round A, round T plus A or tau equal to 0. If you have such kind of equation, so then now this is nothing related with your time derivative. You know it. Yes. Once you have A, then tau is also assumed that tau is a constant. Then now let's say that this is your time derivative. Then you know it in this way. The solution is given by certain coefficient, yes, and exponential minus t and tau. So please try to insert this trial solution into your system. Then you will find that actually this time derivative leaves a itself and multiplied by minus 1 over tau, and that cancels out the second term, so you can easily understand that really satisfy the differential equation in your application. So now you can say that, okay, if we have this kind of behavior, then we will have, yes, just to exponentially decaying output or decaying solution as an action of this differential operator. Then let's try to let's try to discretize it. So in order to make it simple, I just consider A is a constant. We have no further dimension like spatial dimension. However, later you can easily expand it to partial differential equation. For while we are now just looking at the ordinary differential equation because spatial dimensions are neglected. But please understand this situation. Then think about this one. Now we have time I. At time I, how can you discretize this equation? Could you please? So let me just do it in this way. A sub I, it means that A evaluated at time t sub I minus A I minus 1, and delta t. Please note that this delta t is defined as the time difference between t sub I and t sub I minus 1. Then here you can say A I tau. So are you with me? So since we are working at t sub I, this instantaneous term is just used the quantities at time equal to t sub I, and we have used the Euler form for our time derivative. Wow, great. Then how about this? So can you evaluate its solution? Already it is now discretized. Now you can solve it because that is not related with any kind of a matrix inversion. So hand calculation is quite much easy. So let me just do it together with you. In this case, just take the coefficient of A sub I. A sub I will be just 1 over delta t plus 1 over tau, and let's just collect the coefficient for A sub I minus 1. In this case we will have 1 over delta t only. So if you have any question, then please let me know. So from this one, now you can say that A sub I, A evaluated at time t sub I, is simply given by I minus 1 and multiplied by 1 over delta t, 1 over delta t plus 1 over tau. So you know that delta t or tau are assumed to be a positive quantities. So now you can find that this is less than 1 and a positive number. So now A, when we make a time matching, A quantity is decreasing, and at each time step it has a constant reduction factor, so the quantity will be reduced and reduced and reduced further. So that is the application of Euler method to our system. Okay. Do you have any question? Okay. Then let me just do it once again with a different way. So up to now, I have told you that round A over round T can be approximated as delta T equal to 0, delta T A T plus delta T minus A T. Yes, that is, so that is something like a del of T, something like T I plus 1 T I A T I plus 1 minus A T I. But how about this? So also we can consider this is, if this is the reference time, we are taking the difference between the present time and past time or future time. So but here, once again, think about this one. Here, when we have this form, we are now taking the difference between a I and a I minus 1. So here we have yes, that is possible, because anyhow t sub I and t sub I minus 1 are assumed to be close enough, so taking this one can be an approximation for our time derivative. But what I wanted to say right now is think about this simple counterexample. So let me just draw a parabolic curve, this x and y, and let's say that this is certain curve we wanted to take the derivative. So say this one, and this is corresponding to your xi, and let's say that this is corresponding to your xi minus 1. So the philosophy shown here looks like this. We take the difference between these 2 points, and also takes the difference between these 2 points, and we will just the ratio between this and that. So this slope is calculated by our approximation. So you can easily understand the actual evaluation point position is not strictly attached to this x sub I, but it is more appropriate to interpret as it is the derivative defined at x sub I minus 0.5. Yes, maybe this midpoint will be the best suitable point for our derivative. Anyhow, but we are now looking at this point. So yes, although the observation point is slightly different by amount of half difference, half interval, but we are now applying this one. Then in equal ways, if you are asked in this question, how can you answer? You have also x sub I plus 1, then you will have a certain value located here. Then taking the difference between x sub I and xi plus 1, then you take the difference and you take the difference of your function value and calculate also once again the difference, so or slope. Then this slope is yes defined at the midpoint, for example x sub I plus half. Yes, also this is not an exact way to evaluate the derivative at x sub I. But my question is, okay, I know this is not exact. However, in this case, if this guy can be used, or if this guy can be accepted by our time matching step, then why should we reject the use of this guy? Can you find a reasonable justification? So maybe not. So my question is, instead of this red box discretization, now we can try this way. A I plus 1 minus A I and delta t. Of course, we are now assuming that this delta t now should be regarded as the difference between t sub I plus 1 and t sub I, not t sub I and t sub I minus 1. But anyway, if we introduce uniform time differences, then delta t can be shared between these two approaches, and yes, instantaneous value can be written as in this form. Of course, you feel that something is wrong, but yes, at least in staging, you cannot find any reason why we should avoid this approach. So this guy just consider the present value and past value and try to calculate the first derivative. Maybe this first time derivative will be best suitable for at time t sub I minus half, and maybe this guy can be best suitable for t sub I plus positive half. None of them is perfect. They have slight shift from the viewpoint of midpoint of evaluation. So now let's move to this way. So since we have no reasonable objection about this approach, then let me just proceed in the same way. Then in this case, we can find that a I plus 1 coefficient can be just 1 over delta tau. And now you go to this t sub I coefficient. So t sub I coefficient, now it becomes 1 over delta t minus tau. Then now you can find that in this approach, I plus 1 can be written as AI and 1 over delta t minus 1 over tau, yes, and 1 over delta t. That will be the case you take out of your different approaches for discretizing time derivative. Okay, so I think that up to now, although a little bit curious why we have to avoid this guy and have to use this guy, but anyway, the calculation procedure is so simple, and you find that both of them work. But point is, please look at this one. This one is always guaranteed that you have the coefficient or reduction factor which is less than 1. So always the A solution is diminishing. But think about this one. Unfortunately, let's say your delta t happen to be equal to tau, then what will happen?
Zero.
Yes, it becomes 0. Yes, then think about this one. Your delta t is now even longer than tau. Then you will have, in this specific case, you will have 1 over 2 tau minus tau and 1 over 2 tau. So you will have just minus 1 or reduction factor. So what will happen? Reduction factor minus 1 is, if you start from 1, then your next step will be minus 1. And your next step will be once again. That will be your discretized solution. So can you accept this solution? No. This is just oscillating, and this is far from the physically correct solution, like exponentially decaying solution. So then is this approach is completely wrong or no? As you know, if our delta t is much shorter than tau, then now you say that this is much larger than this 1 over tau. So still we will have the reduction factor smaller than 1, and in this case they will be the same. So they share their behavior. So point is, in this left written formulation for time derivative, we have to be careful about this calculation. Okay. Yes. So let me just say finally about this discussion. So the right side, this kind of approach for discretizing your time derivative, that is called as implicit method, and this is corresponding to explicit method. That is the point. Okay. So now you can easily understand, when you use this implicit method is always stable and your solution decay always. However, in the case of explicit form, then you feel that you have to be careful about finding out the time difference between your two time instances. So that is one thing, but here we have a more important difference. Think about this one. Here, although we are now looking at this simple, just ordinary differential equation, but now think about the partial differential equation. Then which one becomes complicated? Now you can easily understand this 1 over tau and this 1 over tau now becomes your more or less your Jacobian matrix. Now this 1 over tau term is really becomes a matrix which has huge dimension and difficult to invert. Then please have a look at this part. In this part, where do we have 1 over tau? Yes, here we have 1 over tau here. And in the right side, where do we have 1 over tau? Here we have 1 over tau. Then, this sounds really obvious, but please have a look at. Since we have 1 over tau here, in this formulation, 1 over tau can be found in this denominator term, and since we have tau here, 1 over tau here, now we can find 1 over tau in this nominator term. So what is this? If we consider a matrix system, then in this part there is no matrix inversion. No matrix inversion. But in this case, since 1 over tau is located in this nominator term, so we need matrix inversion. So if you remember the time you have spent for getting the DC solution, you now realize the importance of this difference. So in the case of an implicit time matching scheme, you have to make the inversion of your Jacobian matrix. Yes, and this Jacobian matrix is slightly modified by this 1 over tau, 1 over delta t term. Yes, so now you have to make an inversion of slightly modified Jacobian matrix. However, in the case of your explicit time matching, you don't have to make inverse of your Jacobian matrix. So that is the huge difference. Then at first glance, you will be really persuaded by this explicit scheme. Oh, then I can live without this time-consuming Jacobian inversion. I can kick out that time-consuming part. That sounds really great, but there is a hidden cost. What is the hidden cost? As I told you before, in order to be stable, the delta t should be much smaller than tau. Then what is tau for our device system? That's the problem. So unfortunately, the tau for our semiconductor device is really extremely short. Tau is so short. So if you really wanted to make any kind of reasonable simulation, then your delta t should be also extremely short. So when I say extremely short, it is a kind of femtosecond. Yes, so it is not acceptable for your application. For example, you wanted to simulate 1 megahertz signal, but you have to spend 1 femtosecond differences. Yes, of course there is no matrix inversion, but anyhow you build the Jacobian and yes, evaluate it. So that cannot be endured by the developer and users. So that is completely useless for our conventional device simulation. But point is, then from the viewpoint of overall computational microelectronics, explicit scheme that is not used at all. No, there is a certain applications or certain simulation scheme where the explicit scheme is widely used. For example, if we are considering the so-called Monte Carlo method. So have you heard about Monte Carlo method? So of course, Mr. Park have heard about Monte Carlo method, but this is not the right context in our current discussion. So when I say Monte Carlo method, in this case, Monte Carlo simulation of the Boltzmann transport equation. So when you consider the Boltzmann transport equation, then typically we adopt the Monte Carlo method. No, Monte Carlo method itself is just a name for describing method with random numbers. So generate certain random numbers to mimic a random variable, then yes, collecting many samples for repeated simulation, then just to say that the ensemble average of these simulation is corresponding to the proper description about the system. So Monte Carlo itself is just saying that random number, and when we apply it to the Boltzmann transportation, so in our computational microelectronics, since this is so widely used, so when you just say Monte Carlo, then people understand that this is the Monte Carlo simulation for the Boltzmann transportation. That has been a standard way to calculate the Boltzmann transportation. In this case, they do not use this implicit method because in this case that takes too long, because inside this system anyhow, due to the scattering, the time difference can be quite short, so we cannot increase the time difference for our Monte Carlo simulation like 1 millisecond or 1 microsecond. That's not possible. Internally in the Boltzmann transportation, there is an event called scattering, and the mean time between these two scattering events is extremely short. So anyhow, we have to use quite frequent update for our status. So update means that repeatedly solve the Poisson equation, and solving the Poisson equation is not possible with explicit steam so many times. So they just use explicit steam. However, our major application is drift diffusion case. Then in this case, we can hide the internal physics behind the scene. So in this case, we can increase the time difference between two time instances quite largely. So millisecond, or depending on the situation, we can even consider second dependence, second scale difference. So in this case, it is not appropriate to use the explicit form, so we have to use implicit form. So now let's go to my final description. So where can you find the time differences? So in your electron continuity equation and in your whole continuity equation, now you can find this term. Then you have to discretize this term with the implicit time scheme, and T and Ti and Ti minus 1 divided by Ti and Ti minus 1. That should be implemented in your code. Also, P takes the same approach. P Ti minus 1 Ti minus Ti minus 1. That should be included in your system. Of course, please note that in your discretization, you always make the integration over the control box. So just putting this term in this form is not suitable. So first of all, you have to also integrate this time derivative term over your control box omega. So that is always understood. So please do it correctly. So my question or my suggestion is, please calculate this one. In the case of a Poisson equation, you don't have to do anything, because Poisson equation is actually instantaneous equation. So you can easily consider the Poisson equation without any modification. Okay, so please perform this homework by next Tuesday. Then yes, now in next lecture we will move to the AC simulation instead of this fully time transient simulation. Okay, thank you, and let's wrap up today's